Hello everyone, welcome back to Electrology, your one-stop destination for all things electrical engineering. In our last video we talked about arcing ground in ungrounded neutral systems. If you haven't watched that yet, make sure to check it out. The link is right in the first comment below. In today's video, we'll understand a very important and effective solution to the problem of arcing ground, and that is arc suppression coil grounding, also known as resonant grounding or Peterson coil grounding. Let's get started. We've already seen that capacitive currents are responsible for producing arcing grounds. These capacitive currents flow because capacitance exists between each line and the earth. Now, if an inductance L of appropriate value is connected in parallel with the capacitance of the system, the fault current IL flowing through L will be in phase opposition to the capacitive current IC of the system. If L is so adjusted that IL equals IC, then the resultant current in the fault will be zero. This condition is known as resonant grounding. An arc suppression coil, also called the Peterson coil, is an iron cord coil connected between the neutral and earth, as shown in the diagram. The reactor is provided with tappings to change the inductance of the coil. By adjusting these tappings, the coil can be tuned with the capacitance of the system. In other words, resonant grounding can be achieved. Imagine a three-phase system employing Peterson coil grounding. Suppose a line-to-ground fault occurs in line B at point F. The fault current IL and the capacitive currents IR and IY will flow as shown. Here, IL flows through the Peterson coil to the neutral and back through the fault. The total capacitive current IC is the phasor sum of IR and IY. The voltage of the faulty phase is applied across the Peterson coil, so the fault current IL lags the faulty phase voltage by 90 degrees. This current IL is in phase opposition to the capacitive current IC. By adjusting the tappings on the coil, the resultant current in the fault can be reduced. If the inductance of the coil is adjusted in such a way that IL equals IC, then the resultant current in the fault will be zero. For resonant grounding, the system behaves like an ungrounded neutral system, so full line voltage appears across the capacitors CR and CY. That means IR equals the square root of 3 times VPH divided by XC. So IC equals square root of 3 times IR, which means IC equals square root of 3 times the square root of 3 times VPH divided by XC, giving us IC equals 3 times VPH divided by XC. Here, XC is the line-to-ground capacitive reactance. Now, the fault current IL equals VPH divided by XL. Here, XL is the inductive reactance of the arc suppression coil. For resonant grounding, IL equals IC. So we substitute VPH divided by XL equals 3 times VPH divided by XC. Cancelling VPH from both sides, we get XL equals XC divided by 3. Now omega L equals 1 divided by 3 omega C. So finally, L equals 1 divided by 3 omega squared C. And that gives us the value of inductance L required for resonant grounding. Now, let's look at what makes this method useful. One big advantage is that when resonance is properly tuned, the arc suppression coil completely neutralizes the capacitive fault current. That means the chances of arcing ground are greatly reduced or even eliminated. Another key point is that this method allows the system to continue operating even during a single line-to-ground fault. That's because the fault current is minimized and doesn't cause damage, so there's no immediate need to trip the system. Also, since the coil is connected between the neutral and earth, it improves system stability and reliability, especially in high-voltage networks where even a minor disturbance can have large effects. However, this system has a few limitations too. The main drawback is that system capacitance doesn't stay constant. It can vary with the number of lines in service, their length, and even environmental conditions. So, to maintain resonance, the coil's inductance needs to be adjusted frequently, which can be a bit of a hassle. Another issue is that for accurate neutralization, transposition of transmission lines is necessary. Without proper transposition, the system capacitance becomes unbalanced, which throws the resonance off and reduces the effectiveness of the coil. So while the arc suppression coil is a powerful tool, it does require careful adjustment and system design to work optimally. And that brings us to the end of this topic. Arc suppression coil grounding, also known as resonant grounding. If you found this video helpful, please like, share, and subscribe to Electrology for more detailed and easy-to-understand videos on electrical engineering topics. Got any questions or suggestions? Just drop a comment below. I read and reply to all of them. If you'd like to support the channel, you can click the thanks button for a one-time contribution or become a channel member by clicking the join button to get exclusive perks and early access. Thanks for watching, and I'll see you in the next one.